Now we will start our chapter 4, that is shear, bond and development length. A beam is subjected to transverse load is subjected to shear force and bending moment. Suppose, let me explain in brief. Suppose this is a beam, there is a transverse load, that means it will undergo shear force and it will undergo bending moment. Simple. Okay. So now let's go for our next shear stress. All of you can see here the cross section of the beam having width B, effective depth D. Let me show you. This is the effective depth. So we have to find out shear stress at a distance of y meter from the neutral axis. This is our neutral axis. What is the formulation? FA y bar by IB, where Q is the shear stress, F is the shear force at section XX. Let me show you. So suppose this is the beam, this is neutral axis, this is width, this is effective depth, this is overall depth. Okay. So we have to find out neutral axis, we have to find out shear stress at a distance of y meter. Suppose this is x-axis. So we have to find out shear stress at section x-axis. Okay. How to find out? The formulation is shear stress is equal to F A y bar by I. What is F? F is the force at section x-axis. Shear force. Okay, A is the area, this area, this depth and into width, this is the area. Y bar, suppose this is the CG of this section. From this CG to neutral axis distance, this is y bar. What is I? I is the moment of inertia of the whole section about neutral axis. And B is the width of the section. Okay. Next. As per IS 456, tau V is equal to BU by BD. Tau V is the nominal shear stress. B is the width of the beam. D is the effective depth of the beam. BU is the vector shear force of the section. Suppose you can see. You can see here, this is the IS code, page number 83. Nominal shear stress is equal to tau V, that is equal to V by BD. If you multiply 1.5, this is vector shear force. Okay. For design, we will use V by BD. Next. So here you can see a beam with a transverse load, and we have taken three elements, element 1, element 2, element 3. So here bending moment will be maximum, shear force equal to 0. Here shear force is maximum, bending moment is 0. Here failure will be vertical crack. Here at point 2, at element 2, this will be inclined crack. That is inclination is nearly 45 degree. Okay. Now we will move towards nominal shear stress in RC section. As I have already told you, nominal shear stress is equal to tau V, that is equal to BU by BD as per IS 456. As you can see here, this tau V is equal to BU by BD. Okay. Next, design shear strength. Design shear strength of concrete. Design shear is the actual shear strength of the structure which it can resist. Point number 2. Tau C can be found out from IS 456 table 19 by calculating percentage of steel and comparing with the grade of concrete. Let me show you table number 19. Then we will know how to find out tau C. This is the IS code. This is table number 22, table number 21, table number 19. Okay. This is our table number 19. Design shear strength of concrete. Tau C. Design shear strength. First, what we discussed nominal shear strength tau B. This is design shear strength tau C. Unit is Newton per mm square. This is page number 73 of IS code. This is page IS 456, page number 73. So here how to find out tau C. Suppose various concrete grade are given: M15, M20, M25, M30, M35, M40 and above. What we have to do is we have to find out percentage of steel, that is AS by BD into 100. AS is the area of steel, that we have to written is AST divided by width of the steel into effective depth of the AST by BD. So AST is the area of the steel, B is the width of the beam, B is the effective depth of the beam into 100. So let me show you how to find it out. Suppose this is a cross section of the beam. This is the neutral axis. Here steel bars are there as the tension zone. This is compression zone, this is tension zone. Suppose 4 number of steel bars of diameter 5. Okay. This is the width of the beam. This is the effective depth of the beam. So area of the steel is AST is first area of the one bar, that is pi by 4 phi square. Now area of the 4 bars, pi by 4 phi square into 4, that is pi phi square. Okay. Now for percentage of steel it is written as PT, that is equal to AST divided by BD into 100. So pi phi square divided by width of the beam into effective depth into 100. In this way we find out percentage of steel. So what will happen? So we will get these values. Okay, suppose our values came 0.8, but there is nothing like 0.8 here. So we will do, our concrete grade is suppose M20. So there is nothing like 0.8, so we will take 0.7 and 1. So for 0.75 respective tau C is 0.56 for M20, and for 1% of steel, that is tau C is 0.62. So we will interpolate 0.75 between 0.75 and 1 to find out 0.8 value. Okay, find out tau C value for 0.8. So in this way we will find out what is our tau C value. Okay, so first the most important thing is we have to check, we have to confirm that tau V nominal shear and design shear is less, both should less than tau C max. Both should be less than tau C max. Okay, tau C max, then we can move forward for our design. So what is tau C max? You can see here maximum shear stress. Maximum shear stress is the tau C max. So our three terms, tau V, tau C and tau C max. For various concrete grade, tau C max values are given here. This you can find out from table number 20 of our IS 456. Now how to design how should we design of shear reinforcement? So let's see design of shear reinforcement. First step is to calculate nominal shear stress tau V, as formula is given. Then design shear strength, we have to find out tau c value from table number 19. Okay. Then tau c max value table number 20. Okay. Then we have to find out the minimum shear reinforcement. The formula is ASB by BSB should be greater than equal zero point 0.4 divided by 0.87 F. ASB total cross sectional area of stirrup leg. Total cross sectional area of stirrup leg effective in shear. SB is spacing of stirrups, B is width, Fi is the yield stress. So our formula is ASB divided by BSB should be greater than equal 0.4 divided by 0.87 Fy. So minimum shear reinforcement. The formulation is ASB by BSB is greater than equal to 0.4 divided by 0.87 Fy. From where did you get this formulation? Here. We got this formulation from page number 48 of IS 456, clause number 26.5.1.6 minimum shear reinforcement. The formulation you can see here. Okay. So ASB is equal to total cross-sectional area of stirrup leg effective in shear. SB is the spacing of stirrup, B is the width, and Fy is the yield strength. We will discuss in later while solving the numerical problem. Okay, next is maximum spacing of stirrup. So maximum spacing of stirrup of vertical stirrups. Stirrups are of two types. One is vertical. For this is beam. This is main reinforcement. This is our vertical stirrups. Okay. Yeah, and if this is beam, this is our reinforcement. This is our inclined stirrups. So maximum spacing of vertical stirrups, that is the SB, the stirrup to stirrup distance, should not be greater than 0.75 D or 300 mm. So first we have to calculate what is the value of 0.75 D. Okay. Then we have to compare which one is lesser, 0.75 D or 300. Again we have to compare that value with the spacing. If spacing is less than from that value, that is okay. Okay. Similarly, in inclined stirrup, stirrups are inclined at 45 degree. This is 45 degree. This is SB spacing. SB. Maximum spacing should not be greater than D or 300 mm, whichever is less. So we have to first calculate D. Then we will compare D and 300, whichever is less. Then we have to compare SB should be less than D or 300 mm. Okay, this is the criteria for deciding the spacing. Okay, in shear design. Next, we will move to case 1, design of shear reinforcement. When tau v is less than tau c, okay, when tau v is greater than tau c, shear reinforcement is to be designed. But when tau v is less than tau c, no shear reinforcement should be designed. Okay, okay, fine. So how to design the shear? Let me show you in IS code. Shear design, we will see. Okay, shear design, let me show you. Okay, yeah, what is that? Okay, you can see here. You can see this is our formula for nominal shear stress tau v. Okay. So with shear reinforcement, under no circumstances shear reinforcement shall the nominal shear stress in beams tau v exceed tau c max. So tau v should be always less than tau c max. In addition to that, tau c also should always be less than tau c max. Okay. Minimum shear reinforcement. When tau v is less than tau c max, minimum shear reinforcement shall be provided. When tau v is less than tau c max, minimum shear reinforcement formula is ASB by BSB should be greater than equal to 0.4 divided by 0.87 Fy. But when tau v is greater than tau c, what we can do? We can provide two type of shear reinforcement. One is vertical stirrups and one is bent up bars. Okay. So I have already told you how to calculate tau c from this table number 19. We have to find out the percentage of steel PT. We have got the concrete grade. So for what value of PT, and by taking the PT value and taking the concrete grade, we can find out the tau c value. If our PT is not in the list, we can interpolate the two values to find out exact tau c. Okay, and from here we can find out tau c max, maximum shear stress, from this table number 20. So what will happen when bent up bars are provided? Their contribution towards shear resistance shall not be more than half that of total shear reinforcement. So bent up bar contribution should not be more than half of the total shear reinforcement. Okay, we will use this clause in our calculation, problem calculation. Okay, next, shear reinforcement shall be provided to carry a shear equal to Bu minus tau c Bd. This is BUS. Shear reinforcement shall be provided to carry a shear equal to Bu minus tau c Bd. This is BUS in our formulation. So for vertical stirrups, the formula for BUS is 0.87. So we have got BUS, that is Bu minus tau c Bd. Okay, so that is equal to this value. We know Fy, we know D, we know ASB, so we will get SB, spacing of stirrups. Okay, from this is for vertical stirrups, and this is for our inclined stirrup. Okay, this formula is for inclined stirrups. Next, for single bar or single group of parallel bars all bent over the same cross section, this is the formulation. Okay, next go to the our note page. Okay, so we know BUS is equal to Bu minus tau c Bd. Okay, so for vertical stirrup, the formula is Vs is equal to sigma SB. What is that? This is 0.87 Fy. So in problem, in IS code, the value is given as BUS is equal to 0.87 Fy ASB D divided by SB. From this we got SB. Okay. So if the bars are bent up, if bent up bars are used, this is the formula. So the formula is given here, 0.87 Fy this is the formulation for bent up bars, 0.87 Fy ASB into sin alpha. So this is 0.87 Fy ASB into sin alpha, where for bent up bar this BUS should not be, for bent up bars this value should not be greater than total shear value divided by 2. This value should not be greater than total shear divided by 2, where alpha is the angle between bent up bars and the member axis. Okay. For the balance, Vs minus Vs star, Vs dot, for the balance value, what is that? This is Vs dash. Okay. So total shear is Vs. So remaining is Vs minus Vs dash, design for vertical shears. So we have designed Vs dash for bent up bar. So what is the total remaining? Vs minus Vs dash. We will use that value for vertical stirrups. So let me tell you what is happening here. Suppose this is our beam. This is main bar. Suppose we have used vertical stirrups. We have used vertical, and along with that we have used bent up bars. Bent up bars shear value is Bs dash. Okay, for vertical stirrup this is, so total shear is Bs. Okay, total shear is Bs. What is the remaining? Remaining is Bs minus Bs dash. So Bs dash portion shear goes to our bent up bar. So this portion will go to our vertical stirrups in shear design. Okay. Okay. For inclined stirrups, this is the formula as given is the IS code. VUS is equal to 0.87 Fy into ASB into D into sin alpha plus cos alpha divided by SV. Okay. So for case 2, when tau V is less than tau C, nominal shear reinforcement is to be provided in form of vertical stirrup. Formula is this. So we have to check minimum reinforcement. Minimum reinforcement if tau V is less than tau C. Okay. If tau V is greater than tau C, we can provide vertical stirrup, inclined stirrup, or bent up bars as discussed earlier. So this is our numerical problem. Question is, a reinforced concrete beam of 400 into 600 mm effective is simply supported and carries a UDL of 60 kN per meter, including self weight over a span of 6 meters. The section is reinforced with 5 number of 20 mm diameter bar. Use M20 and mild steel Fe250. So design shear reinforcement for the beam using vertical stirrups. Second point is 2 bars are bent up at 45 degree at support. Okay, 2 bars are bent up. So for vertical stirrup design, first is our vertical stirrup. How to design vertical stirrup? The width of the beam is, this is the beam, the width is 400 mm, effective depth is 600 mm. L is 6 meter, this is our 6 meter, and UDL is 60 kN. This value is 60 kN. From this beam, we will get our shear force value and bending moment value. For UDL, shear force is, shear force diagram, bending moment diagram, you can see here the maximum value is WL by 2, and for bending moment this is maximum value at the center is WL square by 8. Shape is parabolic. Okay, so our shear force value is 180 kilonewton, that is 180,000 Newton. Okay, so we got our VU. Okay, so from this we will get tau V, that is VU by BD. We got it at 0.75 Newton per mm square. 0.75 Newton per mm square. We are taking M20 grade concrete. So for M20 grade, tau C max is 1.8 Newton per mm square. So for first design criteria is tau v should be always less than tau c max. This satisfy here. 0.75 is less than 1.8. Then okay, then we will move forward. We will find out now tau c. Area of steel. How many bars have been used here? High number of 20 mm diameter bar. So area of the steel is 5 into pi by 4 20 square 1570.7 mm square. So percentage of steel from this formula AST by BD into 100, that is equal to 0.65 percentage. Okay, so 0.65 percentage, as there is nothing like this 0.65 here. You can see here, let me show you. This is the table number 19, from where we will calculate our for tau c. There is nothing like point C, so we have taken M20. So this is 0.5, this is 0.75, so the value is 0.48, this is 0.56. So we have to interpolate between these two values, 0.5, 0.75, 0.48, 0.56. Okay, then we will find out the value of 0.65. Okay, so what we got that is 0.32, but our tau v is 0.75, so 0.75 is greater than 0.32, so shear reinforcement is required. If the case was different, like tau is less than tau c, so we have to check minimum shear reinforcement. Okay, but our case is like tau is greater than tau c, so shear reinforcement is required. Here we will provide vertical stirrups as asked in the question. So our shear force BUS is BU minus tau c BD. We got 103.2 kilonewton. We have to use BUS, that is BU minus tau c BD. The value is 103.2. So you might have some doubt, this is B, no, this is BU, because we have taken this as BU. The UDL value is factor already, that is factor. So this is BU. Okay, so the value is BU minus tau CBD, the value is 103.2. So for this shear force, we will design our shear reinforcement. The value is 103.2. Before going to next step, let's discuss something on vertical stirrups. So you can see here, this is a T section. This is one leg stirrup. This is two leg. This is four leg stirrups. Okay, this is one leg stirrups. This is two leg stirrup. This is four leg stirrup. So for this problem, let's provide 10 mm diameter two leg stirrups in the beam, because our is a beam section. So we will provide two leg stirrup. Suppose the diameter of the stirrup is, so if this is stirrups, suppose this diameter is 10 mm. Okay, so area of the stirrup is, that is ASB. Two leg means we have to multiply 2 into 10 mm diameter stirrup, so pi 4 into 10 square. So value is 157.1 mm square. Okay, so already our formula is VUS is equal to 0.87 Fy into ASB into D divided by SB. So we need SB, so we will move SB here and VUS here. So this formula will be like this. So SB is 127.8, that is nearly 120 mm. So this is the spacing between stirrups to stirrup in our beam. But we have to check it again, as this is vertical stirrup. So the stirrups, the SB should be less than 0.75 D or 300, whichever is less. So 0.75 D is 450. So between 450 and 300, less is 300. 300 is less. So as per provision, our SB should be less than 300. So 120 is less than 300. Hence, okay, this is satisfied. Okay. Next, maximum spacing. So maximum spacing is 210. Okay. The formula, from which formula? That is ASB by BSB should be greater than or equal to 0.4 by 0.87. In fact, from this we will get SB. So this is the formulation for maximum SB. We got it as 210 mm. Next, zone of maximum spacing. So as this is UDL beam, so our shear force diagram is like this. This is our WL by 2 value. Okay. So this is our VU and this is our tau CVD. Okay, tau CVD. You remember, I think VUS is equal to VU minus tau CVD. For this zone, we have to calculate our maximum zone of maximum spacing. So this is our VU. This is our tau CVD. So this zone we have to design for. This is the zone for maximum spacing. So our tau CVD is 76.8. So VU is 180. Tau CVD is 76.8. So we have to find out this distance. How much this is from our this point O. Okay, so X total length is 3 meter. Total length is our, what is the value of our L? The L value is 6 meter. Okay, so if this is 6 meter, this is our beam. This is 6 meter, so this is 3. This is 3. This is the zone required. What is this? So we can take similarity of triangle. Okay, we can take similarity of triangle. So 76.8 divided by X. Okay, again 180 divided by 3. So X is equal to 1.28. So design length is 1.72. So our final answer is, so this hatching portion is our design zone. This portion is our design zone, that is VUS zone. Okay, that is VU minus tau CVD zone. So provide 10 mm 2 leg stirrups at 120 mm center to center up to 1.72 mm from support and 10 mm 2 leg stirrup at 210 mm center to center in the remaining portion, middle zone. So this is the answer. This is our required beam. This is 6 meter. This is 1.7872 meter. This is our shear design zone. Shear design zone. Okay, which zone? VUS zone 1.72. This is also from this side. This is shear design zone 1.72. 10 mm 2 leg stirrup as 120 mm center to center. So stirrup gap are 120 mm from each other. So remaining portion is our, this remaining portion here, stirrups are at position of 210 mm center to center, because remember we have calculated maximum stirrup spacing, that is ASB by BSB 0.45, 0.87. From there we got 210, so this is that 210 value. Okay, this portion is our shear design zone. Again I am telling you, this is our required design zone, vertical stirrups are used. Okay, this is our zone, VUS zone. Okay, and remaining is the manual stirrup spacing is 210 mm. Okay, next, using two number of bent top bars. So there are how many bars? 5 number of bar. When we use two number of bent top bar, remaining bar are 3. So let me tell you, suppose this is a beam, this is a bent top bar. Bent top bar are provided at a distance of L/4 to L/6 from support. Okay, so at support how many bars are there? 3 numbers of bar. After deducting 2 number of bent top bar, 3 into power of 20 square, 94.2 mm square. Area of the steel is for that portion is 0.39. From that percentage of steel we got tau c, that is 0.25. So if we got tau c, we can find out tau c BD, that is 60 kilonewton. So shear force resisted by shear reinforcement. So our design zone value is VUS is equal to VU minus tau c BD, that is 180 kilonewton, minus 60 kilonewton, that is 120 kilonewton. For this 120 we will design the beam. So shear taken up by bent top bars, shear taken up by bent top bar, formula is VS dash. Okay, VS dash is 0.87 Fy ASB into sin alpha. So value is 62.191. So our total shear, design shear value is 120. So as per IS formulation, VS should not be greater than VS by 2. But VS by 2 is 60, but VS dash is 62. So our VS dash should not be greater than 60. So shear reinforcement taken up by bent top bar is 60. So remaining shear force, total shear force is 120, bent top bar is 60. So remaining shear force is 60. This 60 will be taken up by vertical stirrups, and this 60 will be taken by bent top bars. Okay. So provide spacing of 8 mm 2 leg stirrups. So suppose we take 8 mm stirrups, 2 legs vertical stirrups. So ASB is 100.53 mm square, spacing is 140 mm, maximum spacing is 130 mm. So maximum spacing should be least of the following: 0.75 D or 300, that is should be maximum spacing should be less than 300 mm. So spacing is 130 mm. Okay, so we have to provide 8 mm diameter bar, 2 leg vertical stirrup at 130 mm center to center throughout the length of the beam along with 2 bent top bar. So first part, how we got tau b, then tau c BD, then VUS. We find out our shear force, that is 120. We find out our bent top bar shear force, shear force due to bent top bar, that is 60. Okay, so remaining 60 will be our vertical bars. So remaining 60 will be our vertical bar. Okay, let me show you. So this is the spacing for vertical bar. Okay, sorry, this is the spacing for vertical stirrups. Okay, and this is the value of that shear force, 60 kilonewton. So this is the beam, you can see here, this is our bent top bar. Okay, this carries 2 number of bent top bar are there. Okay, these 2 carries 60 kilonewton shear force, and remaining vertical stirrups carries 60 kilonewton shear force. Okay, so the gap between vertical stirrup is 130 mm center to center. Okay, so so now the question arises, So now the question arises, what is the position of our bent of bar? Okay, so that is at a distance of L by 4 to L by 6. Suppose our L is 6 meters, so this is 1000 mm from support. L by 6, 6000 mm divided by 6, 1000 mm. So here it is bent of start here. This is L by 6. The value is L by 6. So next thing, assumption limit state of collapse compression. This value is all these things are given in the IS 456. You can find it out from IS 456. Okay. So curtailment and bent of bar. Curtailment means that what I showed you. This is the curtailment of bent of bar. Okay, this is at a distance of L by 4 to L by 6 from support. Okay. Then effective depth of member is D, 12.5. So curtailment is bent of bar are provided at a distance of L by 4 to L by 6 meter from support. Okay. And curtailment is between these two values, D or 12.5, whichever is greater. Okay. Then nominal cover, effective cover, it is already you know. This is the big cross section of the beam. This is B. This is effective depth D. Okay. So this is our clear cover. Okay. Nominal cover. I am zooming it for you. This is our nominal cover. This is the reinforcement. So this center is, if we add 5 by 2, suppose diameter of this bar are 5, with nominal cover, if we add 5 by 2, okay, so here effective cover started. Okay, this is effective cover. Okay, nominal cover plus 5 by 2 is effective cover. Okay. So for nominal cover, for beam it is 25, for column it is 40, for footing it is 50, and for slab it is 50, 15 or 25. For beam this is 25, for column this is 40, for footing this is 50, for slab this is 15 or 25 mm. For slab, for beam this is 25 mm. Okay, with this we completed our shear design portion. Okay, so every formulation is given in IS code, you can follow it. Okay, the formulations are given in from page number limit state of collapse for shear, clause number 40. You can go for clause number 40, then 40.2.3, then 40.3, then 40.4. Okay, table number 19 for tau C, then table number 20 for tau C max. Okay, with this you can design your shear reinforcement for beam. Thank you.